Hi everyone, my name is Corentin Thierry. I work at our BARTEC Houston office in the Analyzer and Instrumentation division, and today in this video we will be discussing one of our flashpoint analyzers from one of our factories in Germany, the FPA-4. Before we dig further into the flashpoint analyzer per se, we will start with a quick introduction of flashpoint for those of you that may not be too familiar with the measurement itself. So, flashpoint is, as you can see here on the screen, defined as the temperature at which the fumes or the vapors of a liquid will ignite under a source of ignition. Such source of ignition can be a flame, a spark, static electricity that generates, again, a spark, and pretty much any source of heat or energy that provides enough to start the flames. In a day-to-day life, flashpoint, at least in North America, is used to define when a product is flammable or not. And the common value used is 100 degrees F or 37.8 degrees Celsius, where products that have a flashpoint above this specific value are considered non-flammable, and products that have a flashpoint below that specific value are flammable. As an example, gasoline is flammable, whereas diesel is not. Now, aside from the definition, you may be wondering, well, how is flashpoint measured? So, flashpoint is measured in the laboratory using the apparatus you see here on the screen. In a nutshell, a sample is put in a container. This container is heated so that the fumes of the liquid get released with the help of the agitator, and then there's the igniter, the source of ignition I was mentioning earlier, that will ignite the fumes. As the temperature rises, the igniter tries to ignite the fumes at a certain frequency, and whenever those fumes catch fire, it is considered that the flashpoint of the liquid has been detected, and it is then recorded as the flashpoint. So why is flashpoint important, you ask? Well, flashpoint is important for three main reasons. The first one is regulatory reasons. So for instance, diesel, per the EPA in the US, has to have a minimum flashpoint of 40 Celsius for it to be considered acceptable to use in roads. Similarly, jet fuel and other fuels also have flashpoint requirements established by the EPA and other agencies around the world. The second reason is quality. If we talk about jet fuel now, turbine engines, such as the ones used in planes, but the same applies for diesel engines that are used in trucks and everyday vehicles, have a flashpoint requirement that the engine is built around. So if the fuel does not meet that requirement, does not have that proper quality, the engines do not operate within their optimal operational range. And the third reason is for safety. As I mentioned earlier during this video, products are designated as flammable or non-flammable depending on their flashpoint. And specifically, the temperature at which a product can be handled, stored, left outside, left inside, will be dependent on the flashpoint. So from a safety aspect, every MSDS includes flashpoint information that is basically used to inform the user as the range of temperature in which it is safe to use the product or not. Now that we've looked at the generics, or the general part, I should say, of flashpoint, how it's measured, why it matters, let's go back to what brought us to this video, the FPA-4 flashpoint analyzer. As you can see here on the right, I have a picture of the FPA-4. It is made of various components, which we will go over quickly. At the top left, you have the circular box with the BARTEC logo. This is the measurement enclosure. This is where the actual flashpoint analysis takes place. In the following slide, we will look at how the measurement is done, but for now, we will focus on the different components of the analyzer. At the top right, you have an electronics cabinet that is purged. This cabinet is where all the electronics are housed, and where we have communication, we have signal treatment, and where we can provide or send the information back to DCS. Lastly, to the middle on the left, we have a part of a sampling system with flow controllers and pressure regulators. And at the bottom right, we have the purge controller, which controls the purge in the electronic housing above, as I mentioned earlier. In this animation, we can see all the main components that are in the measurement enclosure. We start with the main heater, where the sample is preheated before it reaches the detector or the detector housing, to say it like that. In the detector, the sample will drip into a siphon and the fumes will evaporate or will rise and mix with air before they reach the detector. The detector being heated, as the sample along with air passes over, it will combust depending on its flash point. In the analyzer, the temperature of the detector is being monitored at all times. When a new sample arrives with a different flash point, or if there's a difference in flash point of the same sample, the temperature of the detector will change, and this is used to correlate to the change of flash point in the sample. Using this method, the analyzer is capable of monitoring flash point of the sample coming through continuously, very accurately. Now that you know how the FPA-4 looks like, now that you know why it is important to measure flash point, and lastly, now that you know how the analyzer works, let's go over some quick features and benefits of the analyzer. So this analyzer, as I mentioned earlier, is manufactured at one of our factories in Germany. It is rated for Class 1 Div 2 per the NEC CEC or ATEX ICEX Zone 1, and as I've said during the video, uses purge as a protection method, which also means that you need to have some sort of purge gas, whether air or nitrogen, to maintain the area classification. The analyzer is correlative to ASTM D56 and ASTM D93. Because we are doing a catalytic combustion, which is akin to a cold combustion, the full range of measurement is much higher. This analyzer is able to measure flash points up to 180 degrees centigrade, 350 degrees Fahrenheit, and as I mentioned in the previous section, with a high repeatability of 0.1 Celsius or 0.2 Fahrenheit. Lastly, as you've seen in the video, the measurement is continuous, as in it updates every roughly 10 seconds. As I'm highlighting here, the 10-second update for the flash point allows for very, very fine control of, say, blenders, so that the optimum flash point for product is being monitored. The analyzer, due to its technology, also has very low maintenance requirements because there is no soot or coke being deposited on the detector or on the walls of the surrounding detector due to combustion, as you will see in a traditional cup-style D56 or D93 analyzer. The analyzer also carries built-in fault diagnostics and self-monitoring that are able to predict when the catalyst needs regeneration. Although, as I mentioned earlier, the analyzer does not have a high maintenance, over time, soot and coke will still deposit, which requires the analyzer to regenerate the catalyst. This is being done by increasing the temperature of the catalyst to burn out the soot and continue monitoring and operations. This, in line with the low maintenance, ensures extended life and very little maintenance requirements on the analyzer. Recently, we've seen a lot of renewable diesel and biodiesel being produced all around the world. Those type of diesels tend to have much higher flash point due to their chemical composition, but thanks to the extended range that the FPA offers, we can measure pure biodiesel or pure renewable diesel using the technology we've just discussed. Finally, we offer full system integration out of both our factory in Germany and in Chicago for our system, which allows us to provide a complete turnkey solution that includes all sorts of fast loop pumps, sampling probes, recovery system, as need be for the application. With this, I thank you very much for taking the time to listen to me, and I hope to talk to you soon about one of our Flash One applications. Thank you. Take care. Bye-bye.